All right. Now, this is another separation, but this time they're not at rest in the beginning. They're stuck together, moving rightward on a frictionless track, and then an explosion happens to cause them to separate. We're given the mass of the blue cart and the red cart, and we're told that the final velocity of the blue cart after the collision is 1 meter per second to the left, and the red car has a final velocity of 5 meters per second to the right. Let's calculate the magnitude of the initial velocity of the carts together before the explosion. So we're going to be solving for this initial VI term. Okay, I'd like you to take a moment right now, pause the video, and see if you can solve this problem yourself using the momentum table and the examples we've solved so far. Take a moment now, pause the video, and come back when you're finished. All right, so hopefully you've had a chance to attempt this problem on your own. We're going to begin by filling out this momentum table here with the quantities that I know already. In this case, I don't necessarily know the initial momentum of the red car or the blue car because I don't know the initial velocity of either car, but I can write an expression as a placeholder to keep track of what that term will look like. That will be the mass of the red car times that VI term. And the momentum of the blue car will just be the mass of the blue car times VI. I know that mass as an M may look like momentum, but just keep in mind, remember that momentum is a P, not an M. So that is the mass of the blue car, not the momentum of the blue car, that MB. And then together, I know that the system's momentum will be those two things added together, but I don't know what that is, so I'm going to leave that alone for right now. So after the collision, I know that the red car has a velocity of 5 meters per second to the right, so that's going to be a positive 5, and the mass was 8 kilograms. So 8 times positive 5 will be 40 kilogram times meter per second. And then the blue car has a final velocity of 1 meter per second to the left. That's going to be a negative 1. And the mass was 4. So that's going to be 4 times negative 1. That's going to be negative 4 kilogram times meter per second. So together, right, 40 and negative 4 together will make 36 total units of momentum. So I know that before the collision happened, I had to have 36 total units of momentum. So now what I can do is I can look at this before collision column. I'm just going to kind of cloud this. And I'm going to say that the momentum of the red car, right, I'm going to write that term out, plus the momentum of the blue car. And again, VI is the same because they both have the same velocity, is equal to 36. Right, together they form a system, and the momentum of the system before and after is 36. So I'll go ahead and plug in my mass of red and blue car, but before I do that, actually, let me rearrange for my VI term. I'm going to factor out the initial velocity, which will leave me with the mass of the red car plus the mass of the blue car, and that will be equal to 36. And then I'll just go ahead and divide both sides by that combined mass, which I can do, to get VI by itself. Now that I have my velocity isolated, I'll just go ahead and plug in my values and solve. That's going to be 8 was the mass of the red car plus, 4 was the mass of the blue car, and that's going to be 36 over 12. In other words, that's 3 meters per second. All right, so we've just solved for the initial velocity of both cars. If you would like to right now, we can go ahead and just check our work here, see if that works out. If I plug in 3 for the initial velocity, I'll know that the initial momentum of the red car before the collision was 8 times 3. That's going to be 24 here. And then the blue car would be, 4 times 3. That's going to be a positive 12, right? And that does that add up to 36? Yes, it does. Okay, good sign. Then if I look at the change, 24, let's do that in red. 24 to 40 is a change of plus 16. And then 12 to negative 4 was a change of negative 16. In other words, you went down 16 to go from 12 to negative 4. It lost, right? The blue car lost this much. The red car gained that much. And so what happens if one loses as much as the other one gains? The change in the system's momentum was 0. And good. So this all works out. We know that we've solved the problem correctly. All right, this concludes our series of examples solving problems involving collisions and separations using the law of conservation of momentum and momentum tables. Please take a look at Canvas for some additional practice problems to develop your skills.